I'm sorry, I forgot to hit record until we were halfway through the first problem. Sorry. So I remember today. So we're looking at number 4. Oh, that glue is sticky. And our first thing to do is to see what our period length is. So I've already given us a little bit of a clue. This one is indeed a circle. So it has a period length of pi. So this is a circle. So its period is pi. So our angles that we're going to use are going to be the top half of the unit circle, everything between 0 and pi. So our angles are going to be 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, and pi. And our r's we're going to get from 2 times sine of that value. Well, we know most of those signs. Those are all things from our unit circle. We could do that by hand, or we can type them in the calculator. Either way is fine. Make sure your calculator's in radians mode. And if you want it to automatically go to decimal, you put it in classic instead of math print. Most of them got changed back because my algebra 2 kids are all freaking out about how the calculator is doing weird things. So we'll have to change the settings again, which is mode, radian, bottom one to classic instead of math print. And we're just going to fill in our values. We're going to get decimals as well so that we can get these plotted up instead of in radical form. So sine of 0 is 0 times 2 is still 0. I'm going to do sine of pi over 6. Oh, I'm in degrees. I did the same thing. Which is 1/2 times 2, which is 1. Sine of pi over 4, that's our square root of 2 over 2, times 2 is just square root of 2, which as a decimal is 1.4. Sine of pi over 3, that's our square root of 3 over 2, times 2 means it's just the square root of 3 part, which is about 1.7. Sine of pi over 2 is 1, times 2 is 2. And it's going to keep going in that same pattern. In fact, it does the same values, just in reverse, going this way. So we're going to plot up these points. So at 0, 0, we have a point. Pi over 6, 1. Pi over 4, 1.4. Pi over 3, 1.7. And pi over 2, 2. 2 pi over 3, we're at 1.7. 3 pi over 4 is 1.4. 5 pi over 6 is 1. And at pi, we're back at 0. So we have a little bitty baby circle. Questions on that one? The circles aren't bad. Plug and chug for the most part. It's a matter of finding out our period length and just substituting pieces in. Okay. So then we're going to go to the very last one, which is this one. So we have r equals 3 cosine of 2 pi. Everything between 4 and 8 we did yesterday, so if you're missing those, you can go watch the video, which should be uploaded, and the PDF is uploaded and will get re-uploaded with today's graphs included as well. So it's all going to be in the one document. So what kind of graph is this? This is a rows. Does this row have an even n or an odd n? Even, because our n is that 2. So that's our n. So if our n is even, that means we're going to have a period of what? Of 2 pi. So we're doing the whole kit and caboodle. And since our n is even, that means we're also going to have 2n petals. So how many petals is this going to have? 4. So I'm going to jump down to where the max values occur. And those are going to happen when our trig function equals 1 or -1. That's where we're hitting the extremes of it, because it never goes bigger than 1, and -1 is just the radius out the opposite side. So our maximums are going to occur where our cosine of 2 pi equals 1 or -1. So what we're going to do is we're going to solve it old school style. We want to know where this guy equals 1. So we do this with what is essentially a u substitution. We're going to do cosine of x equals 1. And we're going to do cosine of x equals -1. Solving them old school style. So I'm just going to start on my +1. So what values of cosine give us a value of 1? What will our x be? 0. And that repeats every 2 pi. So we're doing this old school style, so we're doing it like for the full forever. So it's going to be 0 plus 2 pi times some random natural, or some natural number. But we don't really care about x. I want to know when 2 theta equals 0 plus 2 pi n. So that's going to happen if we divide both sides by 2. Our theta is going to be 0 plus pi n. So our theta, or our cosine is going to equal 1 whenever theta is 0 or pi or 2 pi or 3 pi or 4 pi, on and on for infinity. However, since we're only working in the period of our function, which goes from 0 to 2 pi, we're going to have maximums at 0, pi, and 2 pi. We're going to do the same thing for our -1. It is the exact same vibe. So this gives us a chance to kind of practice that old school solving before we start doing for realsies final prep next week. So let's do the same thing over here for our cosine of -1. So what is our x going to be to get cosines of -1? It's going to be pi plus 2 pi n. We're still solving it for all of eternity, for all real numbers. We wait until the end to make it fit our period, because 2 theta is what really equals our pi plus 2 pi n. So our theta is going to be pi over 2 plus pi n, because we're dividing everybody by 2. So I'm going to list out some of our thetas. When we're going to have a cosine of -1 will be pi over 2 and 3 pi over 2 and 5 pi over 2 and 7 pi over 2, on and on for eternity. The only ones in our interval here between 0 and 2 pi are our pi over 2 and our 3 pi over 2. What this is telling me is that when we come in here to any of these values, we're going to have our farthest out places. It's going to be the maximum it's going to be. So when our cosine equals 1 or -1, so if our cosine 2 theta equals 1, what is the value of r going to be? What is the farthest out it's going to go radius-wise if this piece is 1? 3. I heard it. It was whispered, but it was there. Our maximum value is going to be 3. When these equal 1, for all of these values, it's going to have a radius of 3. For these ones, it's going to be +3, and for these ones, it's going to be -3. So when we're filling in our tables, I have 1, 2, 3, 4, 5 of my values already filled in. I don't have to put them in the calculator, ready to rock and roll. We can do the same thing with our zeros. I can do the exact same thing to figure out when my cosine of 2 theta is going to equal 0. We do it as a u substitution. I'm just using an x. I'm going to zoom it in. So when does cosine of x equal 0? Pi over 2. And it repeats how often? Does it have to go all the way around the circle to repeat, or does it go halfway around the circle to repeat? Halfway, which means it repeats every pi value, because it hits 0 twice. It'll hit +1 once, -1 once, and it hits 0 twice. So our 2 theta is what really equals our pi over 2 plus pi n. So our thetas are going to be our pi over 4 plus pi over 2. So our thetas that actually hit this are going to be our pi over 4, 3 pi over 4, 5 pi over 4, 7 pi over 4, 9 pi over 4, etc. I can keep going. But the only ones that are actually in our interval from 0 to 2 pi are these ones. We've got our pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Since we're going up to 2 pi, we can stop right there. So again, what this tells me is that for all 4 of these values, when we come to fill in our radius, it's going to be 0. All of them hit 0. So we're going to come and fill in our tables, and we're going to see just exactly how many of these we know. We got to do everything from 0 to 2 pi, so that's my next step is going to be to fill in all my thetas. So we're going to go from 0, pi over 6, pi over 4, pi over 3, pi over 2, 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 3/4 of the way through the circle. We're almost to the end. Oh my gosh, there's so many of these. 5 pi over 3, 7 pi over 4. Where'd my pi go? There it is. 11 pi over 6, and 2 pi. Whew, lots of pieces. But I already know a lot of them. All of my zeros, that's these guys here, these all have a radius of 0. So pi over 4 has a radius of 0. 3 pi over 4 has a radius of 0. 5 pi over 4 has a radius of 0. 7 pi over 4 has a radius of 0. I can fill those in. Where my cosine equals 1, they're going to have a value of 3. So any of these ones, my 0 pi and my 2 pi, are all going to have a radius of 3. So 0, pi, and 2 pi all have a radius of 3. When my cosine equals -1, it has the same value, it's just negative. Yes, dear? Because if we look at our original equation, when my cosine to, oh, that was not the laser pointer. When my cosine to theta equals 1, so when my cosine, these guys were where my cosine equals 1, 3 times my value of 1. So that's why it's going to be 3. But then when my cosine is -1, so when this chunk is -1, for these guys, it's going to be -3. I mean, you can also do this with plugging and chugging, but it also got us to practice our solving stuff, which we haven't done in a hot minute. So our pi over 2 and our 3 pi over 2. So dual purpose. It gets us to think about these in a slightly different way, and it gets us to practice our solving. Oh, snap. Double whammy. Okay, so it significantly reduces the amount of things we need to plug in. When we have a period of 2 pi, instead of having to plug in every single, I believe it's 18 of these values, I have cut that in more than half. So we don't have to plug in all 18. You would get the exact same values. If you substitute like 3 cosine 2 times 0, 3 cosine 2 times pi over 4, you'll get the right values. They'll be the same thing. It was a way to get us to practice our solving again. Oh, snap. Double trickiness. And it gets us to think about them in a way of where are our maximums, where are our minimums. So we're going to fill in plug and chug to get the rest of these values so we can plot it up. So we're going to do our 3 cosine of 2 times pi over 6. Which is going to give us about 1.5. 3 cosine 2 times pi over 3, which is going to give us negative 1.5. When we do our 2 pi over 3 in place of our theta, we're going to get a negative 1.5. When we do 5 pi over 6, we get a positive 1.5. When we do our 7 pi over 6, we get a positive 1.5. 4 pi over 3, we get a negative 1.5. 5 pi over 3 is another negative 1.5. And our 11 pi over 6 is a positive 1.5. Trying to zoom this in. There we go. So we can see everything. All right. So now we're going to plot these up. And one way to think about these when you're graphing is every single piece that's from 0 to 0, that's going to be one petal. This is going to be one petal. This is going to be one petal. And then my outside two pieces here between those first and last zeros, that is another petal. So we're going to start with a half, and then we'll get a whole petal and a whole petal, whole petal, whole petal. So it feels weird because it doesn't feel like we're starting in the middle, because we're not. So angle 0, we have a point at 3. Pi over 6, we're at 1.5. And then we're back into 0. So I've got a half a petal. Then I'm going to take my pi over 3 minus 1.5. It's going to be here. Trying to make it so we can actually see everything at the same time. And it's a balancing act because my iPad views things slightly differently than the screen does. There we go. So then we're doing our pi over 2, negative 3. 1, 2, 3 down here. 2 pi over 3, that's on this angle, but we have a negative 1.5, so it's down here. And then our 3 pi over 4 gives us a 0, so we're at this petal. So this is the one I just did in pink. That was this guy. I'll do this one in green, just so we can see where I'm getting these pieces from. So then we're at our 5 pi over 6. And we're at positive 1.5, which is here. Got our pi, which is 3. And our 7 pi over 6, which is 1.5, to our 5 pi over 4 as 0. So we have this petal. And then I'll do this one in blue just so we can like match things up visually with where they're coming from. So our 4 pi over 3, that's this angle. Oop, sorry, squeaking out. It's this angle. But we're taking a radius of negative 1.5, so it's up here. 3 pi over 2, negative 3, which puts it way up here. 5 pi over 3, negative 1.5, which puts it up here. And then our 7 pi over 4 was a 0. So we get a petal that looks like this. And then finishing up our outside piece, our 11 pi over 6, we have a 1.5. And our 2 pi takes us back out to 3. So we've got our other half of this petal. So this one and this one were all the purple pieces. Okay, so the roses are weird and complicated and obnoxious. But they're pretty. Okay, so the next thing I'm going to show you might make you slightly mad because it's going to be really easy. Because what we're going to do is I'm going to go on to Desmos. There we go. And I'm going to show you how to graph these on the computer. So it's desmos.com. Except helps I type the whole thing in because it got really thrown. There we go. And we can go to the graphing calculator. They do have this available on your phone, so you can do it on your phone. I can't get it to show on the screen as a phone, but I'm going to show you up here. And when you go into the graphing calculator, it automatically goes to a traditional coordinate grid. Like, cool, not super helpful. You go to the little wrench right here, switches it to a polar graph. I'm going to hit the big A that just makes my numbers bigger so you guys can see it better on the screen. So it switches it to a polar graph. It's in the little wrench on the graph. under grid is where it switches to polar. When we're writing our equations to graph these kinds of things, we have to include the R equals, or it's going to do it as a traditional, like it's trying to fit it on a coordinate grid. So if I just put in cosine of theta, which you can write theta, oh no, it gets grumpy. Cosine of x. It just does this, like it puts it on top of there, super gross. But if I come in here and I say R equals cosine of theta, it gives us our circle. I can go 2 theta and make us our flower. I could go 3 cosine and make big circle. 3 plus cosine. There we got our limacon. I could come over here and go squared. Oh, maybe. It's going to get grumpy about it. Oh, I think we don't have a plus on that one. Oh, it doesn't like those. Okay, so it won't do that. I wasn't sure. I hadn't tried that one. Oh, to get those, I guess we'd have to do like square root maybe. I haven't tried. I'm playing around with it right now. Square root, oh, hang on. I'll just, so R equals square root. I'm trying to get the R squared ones. To be fair, I haven't played around with these. Let's do 4 cosine 2 theta. There it goes. You put them in as a square root instead of as an R squared. I don't think it'll let me do it. Let me try. R squared equals 4 cosine 2 theta. Yeah, it doesn't like, it won't let you do it as a square. So for our lemniscetes, you have to put them in as a square root like this, but it'll still let you do it. I could even come in here and do, instead of cosine, do it as a sine and get it to twist. I can turn this one off if that circle is really distracting. You just click on this little color thing here. So I could do an Archimedes spiral. R equals, let's see, 2 theta. And I just type out the word theta and it switches it over because it doesn't have a button. So Theta, and it switches. So it doesn't have a button for it, but it'll give us that spiral. I can then come in here and like say what happens if it's negative. I could say what happens if it's 1, or I could even go 0.5, make it real small. 0.2, dizzy. Okay, so we have all kinds of different ways to do it. And we can put all kinds of different pieces in here. Because what we're going to be doing tomorrow and Monday and Tuesday and then until we finish, the point of finishment is self-decided, is you guys are going to be making these.
I thought we were going to be reviewing for the final.
We have the project first. Then we're going to be reviewing for the final.
When do we start reviewing for final?
When we're done with the project.
Is that for a grade?
Yes, it's going to go into third grade.
Okay. We can work as partners?
You will be doing it as partners. I highly, highly do not recommend doing it individually, and honestly, I don't have enough of these for you to do them individually. So you're going to work with a partner.
Huh?
So I have like 1 or 2 extras just in case we have situations come up. And it'll go into quiz grade. But it's slightly, like it's 30 points instead of 20 points, so it's slightly more than a regular quiz. But you're gonna do it in partners, groups of 2, like not 2, or not 3, not 4, groups of 2. And what you're gonna do is you're gonna need to have at least 4 polar graphs.
What's a polar graph? Oh. Like
The purple and the green
4.
are 2 different ones, right?
So the spiral and the green are 2 different ones.
Okay.
So you're gonna have 4 equations.
Wait, so like this, the row thing like that?
The rows only counts as
I
1.
mean, there's like 4.
You have to include at least 1 rows. Okay, so there's like specifications on here. And I have two different versions of it. I'm trying to see what's different on it because they got printed by two different people.
On paper.
I don't think there's really anything different.
Also.
Oh, it's just that this one says it has to be typed and this one I said you could write neatly. Because you have to include your tables. Okay? So you can have them written tidily with your equation and your full table. Or you can type them and print them out. And what you're going to do is you're going to glue construction paper on a foam board. You're going to glue a polar on your foam board. And we have a big pin for the centerpiece because you use the center a lot of times. So I have, it's called a brad, that you put in the middle so that your center is a little bit bigger and easier to find and easier to use than a tiny, tiny pin. Because everything else comes on teeny tiny baby pins. Okay? So before I pass on any foam or any paper or anything, you and your partner are going to go onto Desmos and you're going to plan it first. We're not just going to fly willy-nilly into this because we'd like to keep it semi-organized and actually readable. I do not want it to look like somebody took this string and just like threw it at the board. Just of string. It needs to actually be readable so we can actually see the picture. And you can get as creative as you want. And there are opportunities for extra points. If we do more than 4 equations, if we do hard things, like go see more than 1 row, we can get extra credit. And this goes into the quiz category. Let's remember that. Extra credit in that quiz category. This might be one of those things that we Yes, dear. So each equation is about 4 points out of the 30 points. And so 2 will point. Like probably we would have 2 that could be extra credit. But like feel free to go creative. I have a gazillion colors of string. I have Miss Brian took my string today to show you my box of string. And tomorrow I'll bring in my big giant cracker organizer of string. Because it's me, y'all. Of course I have embroidery thread. Like, I have miles and miles of embroidery thread. So you're going to work with a partner. So you need to find a partner. I mean, there's some of you that I can already tell who's going to be your partner. Just say, the duo. You guys will work together. I'm sure of it. I was like, you can work with somebody else, but I'm going to be genuinely shocked if you detach from each other. Because y'all look together. So these are the instructions.
This one looks like my neck.
Thank you. It's just as good as a catalog. One of she opened a video with the yeah, it goes back on. It's just like, boop. Like the nail polish. It's a gel, so it's glue. We just super glued it. Or nail glued it technically. I do it myself because I had way too cheap to pay for somebody to do that. It's technically due. When did I say? I want to say technically it's due next Wednesday, the 15th.
Next Friday.
Technically. Next Wednesday, but if we are done early, great. If we need more time, understandable, but then we're getting into final review stuff, which I am actively right now working on putting together the final review with the final next to me, and I'm writing the review.